All right, we'll get this kicked off. Yeah, it's great to be here. So I'm going to be talking about how container orchestration and Kubernetes has changed the way that we're architecting our software and what I think we need to do to try to make it simpler. Start with a little bit about me. Also, I apologize. I'm recovering from a cold, so I've got a little bit of a congestion still finishing. A little bit about my background. I was one of the creators of one of the first container orchestration systems called Apache Mesos. Some of you may have heard of it. It ran at large scale a bunch of companies, including places like Twitter, Uber, Netflix, Apple. Twitter is one of the folks where I worked. It helped really ignite the container and microservices era. These days, we consider it kind of like a BSD to Kubernetes. I founded a company called Mesosphere, where we did lots of great container orchestration, cloud-native things. Perhaps one of my favorites was throwing a great party at one of the KubeCons called Ice KubeCon, where we actually hosted IceCube. And I always like to ask people, has anyone in the audience, was anybody at that party? Bummer. It was a good time. All right. I was one of the founding board members of the CNCF and on the inaugural TOC. And it gave me a lot of time working with a bunch of companies as they were adopting cloud native. Gave me a lot of time to think about what we did right and what we didn't do right. And now I'm working on rethinking how we build applications for the cloud at Reboot. So I've had a fair amount of time to reflect. And I think one of the most interesting reflections I had was that when we were first setting out to build container orchestrators, we were really building them for the operators, not for the application developers. And this talk is going to be at a higher level. It's really focused more on application developers than operators, although I know a large part of the audience is for operators. We're really caring about how people are building applications. You know, we actually asked application developers to split their applications into microservices or lambdas, because that actually made it easier for us, the operators, right? It made it easier for us to do things like turn machines off if we needed to do hardware or software upgrades. Turn machines off if we wanted to consolidate resources, consolidate applications on less resources. But it made it more painful for application developers. So we've been kind of thinking about this idea if Kubernetes really gave infrastructure teams and abstractions for their machines so they could treat them as cattle rather than pets, what are the right abstractions or what are the right primitives that we should be thinking about trying to give application developers so they can do the same thing but for their business logic? Some people might think I'm trying to think about, what comes after microservices. Again, we don't want to throw the baby out with the bathwater. A lot of what's happened in the cloud-native ecosystem is great. We want to leverage that tech as much as possible. We just want to simplify it for application developers. So, maybe it's like, hey, microservices were wrong. Is there something else, some other way that we should be building applications? And some folks might say, didn't we do that? Isn't that serverless? Didn't we simplify it for application developers by just giving you lambdas? And hopefully after today, you'll agree with me that it's not either of these two things. That all being said, microservices, and throughout the rest of this talk, I might just use the word microservices, but if I'm saying microservices, I'm probably referring to both microservices and serverless. They have a ton going for them. Right? Microservices helped developers and organizations build software in a more modular way. Modularity makes it easier to understand, modify, and test your code. It gives organizations engineering agility because teams can operate and deploy their software more independently and autonomously. If your company's into it, it gives you technology diversity behind well-encapsulated APIs. And all these things make it easier to scale your applications and easier to scale your companies. And of course, we all know this. We're at a Kubernetes event. But again, we don't want to throw these properties out. These are critical properties that we still want to instill in the way that people actually build their applications. Yet, most of the organizations that have looked at trying to adopt, say, cloud-native programming practices, have more or less been confronted with a lot of challenges. So much so that Martin Fowler has this great quote, which is, you shouldn't start a new project with microservices, even if you're sure your application will be big enough to make it worthwhile. So there's all this value, and yet there's this wind in our face. And so the conventional wisdom became that most organizations would only adopt microservices when they graduate off monoliths. because that's the perfect time. That's when your product and your company tend to be scaling like crazy, when you actually need them. And that's the perfect time for companies to be like, let's stop and let's do a rewrite into this completely different architecture pattern. It just doesn't make sense, but it's what we've seen with tons of companies. All right, so what was Martin Fowler really talking about when he said, don't adopt these patterns? This is the stuff he was talking about. These are the cloud-native programming patterns that is what application developers have to grapple with that makes their job so much harder. Things like command query responsibility segregation, things like event sourcing, things like sagas, patterns that developers, when they were not previously working in cloud native, the cloud native ecosystem, didn't necessarily have to think about, and now is kind of forced in their faces when they're thinking about how they're going to build their microservices or their Lambda-based apps. There's this great paper called "There's Just No Getting Around It, You're Building a Distributed System." What I love about this paper is it's from 2011. And the distributed system that they were talking about was the distributed system between the front end and the back end. Because the back end was a monolith. And we just made it even more of a distributed system. We made not only the front end and the back end distributed system, we made the back end a complete distributed system as well. And this is why we had to introduce all these new patterns. We had to introduce all these new patterns to solve the fact that we were building a distributed system. But at the end of the day, the goals are still simple. Right? What we're trying to accomplish can really be boiled down to as simple as applications want to write some data and they want to read some data. And ideally, they want to do that without bugs. Right? And the goal of what we really set out to do with what we're trying to do now is we're trying to say, all right, well, at least without the bugs due to the distributed environment. Could we at least eliminate those bugs? Because the reality is you're going to have bugs. We're all going to have business logic bugs. But unfortunately, for cloud-native application developers, instead of spending the time fixing their business logic bugs, they're spending their time fixing the bugs because the software runs in a distributed environment. And I'm going to talk about some of really, I think, the two core examples that, let's start with writes, that really make writes in a distributed system hard. Why are writes in a distributed system hard, right? Really just trying to lay this out. There's two of the biggest reasons. One is what I call the retry paradox, and the other one is just getting consistency right. And so I want to show a couple of examples that hopefully really illustrate why I think we need to do something about this. All right, so the retry paradox. So I'm going to start with this example. I run into these kinds of bugs all the time, so I try to take screenshots now when I think maybe I'm going to be able to demonstrate something that's happening. So this is me trying to deposit a check, and I got an error back that said, failed deposit check, okay, or try again. So naturally, I clicked try again because I wanted to deposit the check. About 24 hours later, I got this wonderful email that said, we were unable to process your mobile check deposit. Please give us a call. So of course, I gave them a call. And they politely, nice woman on support, politely accused me of bank fraud, trying to deposit my check twice. To which I just chuckled and said something exactly once, something item potency, and she said, what are you talking about? And I said, trust me, I was not trying to commit a crime that turned out I just happened to Google afterwards. That's a felony in I think something like 7 states. Okay. So what happened? So this is what I call the retry paradox. Retries are something that becomes so fundamental in everyone that's building cloud-native apps, but there's a catch, which is we want to retry in the event of a retriable error. Retriable errors specifically are, I don't know what happened. But I can't retry if that call happens to have effects because I only want those effects to be performed once, right? This is why so many web pages and so many sites out there, they give you this experience, the please don't close this window or use the back button experience because we can't retry. This was a problem when that original paper was written. There's no problem around it. You're building a distributed system because that distributed system was just between the front end and the back end. It still exists today. It's also one of the fundamental reasons why retries are not turned on by default in most application frameworks because that would be scary. It seems like what you want most of the time, but if they turn it on by default, there'd be a lot more Schwab issues than what we have today. All right, the next one is consistency. So to do this, I'm going to talk about a common example we see, which is e-commerce checkout. And if we were to build it with something like microservices, it would look something like this. And when I first look at this code, there's a lot to really like about this code. Right? It's clear that I've been able to modularize the code into different teams that could own, for example, the cart, the shipping service, the payment service, the emailing service. That's all fantastic. That's what helps our organization scale and move faster. And of course, there's a massive bug in this code. I've just composed all these pieces together. That's also really, really nice. Composition is what makes us productive as programmers. But there's a big bug here. Do we all see the bug? The bug is, what happens if the machine that's running this code happens to fail after I call authorize charge, but for example, before I call ship order? And anybody that has run microservices in anger, they're like, yeah, Ben, of course, we don't do that. That's just not what we do. So why is this happening though? It's happening because the developer's intent when they were writing the code is they just wanted to do the simple thing. They just wanted all this stuff to happen or not happen. And of course, if it didn't happen and somebody retried, or if somebody didn't find out about whether or not it happened and it retried, they wanted it only to happen once, right? Getting back to that previous retry issue, they didn't want it to happen more than once, okay? So there's really kind of two camps that I think people fall in when I give this example. There's the first camp that are like, yeah, of course, we run microservices in anger. We would never do that. I don't even know why you're showing this example. And then there's the second camp of people that are sort of like, I wonder if I have this bug in my own code right now that's running in my systems. And it's not surprising that a lot of us actually fall in that second camp, because this e-commerce checkout, while I put some ellipses and remove some code, is literally taken directly from Google's microservices demo. It is literally where everybody starts, which is writing code that you should never write with microservices in production. It's right there. I check it all the time to see if one day there's going to be an audience member from Google that's going to go back and do something to change this, and it's still there. These are real bugs. Again, this is me taking more screenshots. This was me trying to book a flight with United, and I got an unable to complete transaction. So I clicked OK, left me in the place. I thought maybe it had something to do with my credit card. So I changed the credit card. I tried again, unable to complete transaction. I changed it, a third credit card, fourth credit card, 4 times. I'm like, all right, clearly something's going wrong. About an hour later, I checked my email, and I had 4 emails from United Airlines with an important message regarding my flight. And each one of those messages had its own confirmation number, its own reservation number, and each one was telling me that one of the other ones was a conflicting reservation and that they would be canceling one of them because, I can only have one reservation on the same time. So, we all know what happened, right? We got somewhere in this code. It didn't happen atomically, but we at least got through the step that was, let's go check to see if they have any other reservations that maybe are bad reservations and email them. All right, so we've had to solve these problems. All those programming patterns that I talked about earlier, we've had to solve these problems, and we've done them by introducing things like pub, sub, and queues, all these things that I talked about before, event sourcing, sagas, more and more these days, durable execution as well. And I think it's a good step, because at least we're moving from an inconsistent world to an eventually consistent world. Before, we were just sending emails to users in an inconsistent way. At least now, maybe we won't send those emails because we'll wait for steps by writing all these updates in an event source-based way or in a queue-based way. But it's really risen to this thing that we call internally, the cloud-native collection of software is this queue-glued software. That's how we talk about it. We've just glued all this stuff together with queues, which for the most part has led to an inversion of control in the software, callback hell, except in our cloud native codes with business processes scattered throughout the code base. And there's a reason why modern programming languages have adopted constructs like async await. It's because it's harder to reason about callback-based programming models. It's much easier to reason about a programming model that's not callback-based. It's also, to me, though, ironic that even though we've gone from inconsistent to eventually consistent, we live in an extremely strongly consistent world with databases that have gotten way, way better, that can scale dramatically. Our applications are eventually consistent, even though these high-scale databases are strongly consistent. There's a disconnect here that we're not actually able to take advantage of them. And of course, have these things solved the retry paradox? If at least we've made it so we can eventually consistently get through things, have we solved the retry paradox? And just these on their cover, the answer is no. In fact, most of the organizations that I worked with, even when they implemented these things in their organizations, they still had that problem. And they had to take it a step further, and they had to introduce things like idempotent producers or manual idempotency keys or all these other pieces. All right, so I hope I've convinced you that I think we can do better. And it's what we're trying to do with Reboot. So I want to spend a little bit of time talking about Reboot and what we're building. And I hope some of the ideas here are interesting for the way that you guys all are building your software. If not, Reboot's something that you want to take a look at. So Reboot's a new application framework with a novel cloud-native programming model. So it's a programming model that's trying to directly solve these problems. It's not a new programming language. We've currently implemented it for TypeScript and Python, but it's built on top of gRPC. So I'm at a CNCF event here because we're all in on cloud native. We don't want to throw away all the pieces that we've done in the cloud native ecosystem. So we built this on top of gRPC, and so while we started with TypeScript and Python, it would be very easy for us to add the other languages. So from 100,000 feet, the Reboot program model is very similar to actors in that it encapsulates behavior, state, and communication into a single abstraction that we call a durable data structure. But instead of passing messages, which is how actors tends to work, you call methods, RPC, gRPC. And most importantly, these methods have a well-defined semantics for how they compose together safely. Okay? Instead of thinking in tables and rows when you're building software, you think in terms of these durable data structures that are distributed. We're building distributed systems. These durable data structures are distributed across whatever resources you'd have in your Kubernetes cluster. So Reboot's goal is to make writes in a distributed system easy. The how is that we make effects explicit and we try to eliminate side effects. And so I'm going to talk about what that looks like. Because again, you're going to have business logic bugs. We just want people focusing on those bugs, not their distributed systems bugs. So what's a durable data structure look like? So again, it's built on top of gRPC, and it leverages a lot of the pieces of tech from the gRPC ecosystem. So you describe these durable data structures using protobuf. In the future, we might introduce other interface definition languages as well, or other ways to do it, but for now you build protobuf. So imagine if you're building something like a bank, you would have, say, a data structure, say, an account, which would have things like name, birthday, balance. That's kind of step one. You describe your data structures, and then step two is you describe what operations can be performed on those data structures, things like deposit, withdraw, balance, open. And in particular, you qualify these operations with what they're allowed to do with the state. You qualify them as either being readers, writers, transactions, or workflows. And I'm probably just going to have enough time today to talk about readers, writers, transactions. You then go implement the code almost identical to if you implemented it with gRPC. If you're familiar with gRPC, Reboot will look almost identical to that. Here's just two sides. On the left-hand side is gRPC. On the right-hand side is Reboot. The only difference is that, the main difference, is that in addition to getting the request that's being called, we also inject the state for that durable data structure that you're actually operating on. Okay, so if you had 1 million accounts, when we executed this code, we would be giving you this state. If you're familiar with ORMs, you can kind of think of this in an ORM-like way, where we're getting the data out of the database, we're sticking it into this function call so you can operate on the state. All right, you can construct instances of these durable data structures. You can reference them. So in the gRPC world, that would be like getting a stub. A reference is like a stub when you want to call one of these things. And then, of course, you can call their methods. It looks almost identical to gRPC. We did simplify some things. All the code examples I'm going to give you, sorry I didn't say it earlier, is for Python. All right, now I want to talk about the fun stuff, though. These qualified methods and what makes the different functions that are running throughout your cluster, what makes it safe. So first we have readers. So how do readers work? So readers take an immutable snapshot of the state. We can execute them concurrently, anywhere in the cluster that we'd want. And they can only make calls to other readers. So this is how we're starting to constrain the programming model to eliminate those distributed systems bugs. Okay, so readers can only call other readers. And since a reader's calling a reader and a reader can only call other readers, hopefully inductively, we're seeing that they can have no effects. They can make no state updates in the cluster. Okay, writers. Writers also take the current state. They're executed serially, so they can mutate the state directly. So here I am, I'm just updating state.balance directly if I'm doing something like account.deposit. And they also can only call other readers. That might be weird. As a writer, shouldn't it also be able to call other things that are doing writers? But no, writers can only update their own state and call other readers. Okay? Because again, we're trying to eliminate those partial state updates that you saw in the e-commerce example, where if I had a bunch of writers, I'd get possibly this partial state. So writers themselves can only do that. And inductively, since we already said readers can also only call their readers, we know that the only state updates from writers are coming from the updates directly to its state. Okay, so I want to take a minute to pause and just talk about, like, okay, that all sounds great, but you know, how do you make sure that this is the way people will actually write code in practice? So the first thing we need to make sure is that you only call allowed functions. And we do that because you notice that every single method gets passed a context. And when you want to go call some other method, you have to use that context as well. Again, if you're familiar with gRPC, in some of the gRPC languages, this is just the way it works, not all of them. For us, it always works this way. You have to use whatever context is given to you to call any other methods. So we can enforce this directly via type errors. We can enforce the fact that a writer can't call another writer because here I am trying to call another writer method deposit, and a type system can say, no, you have a writer context, you can't do that. Okay? Or we can give you runtime execution errors if you happen to be using, you know, JavaScript or Python without type checking. Okay? So that's cool. That's how we can actually enforce that. But we also want to make sure there's no other side effects, like someone's not calling out into some other service that doesn't happen to be using Reboot. How do we do that? So we take this little trick that we learned from React, which for those people that have built full stack applications that use React, React is probably the most successful application framework of getting people to program in a safe, side effect-free functional programming style. And one of the ways that they do it is they execute all of the functions during development mode twice. So you learn really, really quickly if you shouldn't be doing something that's not following the React model. And we do the same thing here. So if you happen to, in your writer or in your reader, calling out and doing any other side effects, you learn really quickly. You know, I think there's something really interesting here about the programming language nerds amongst us that would prefer if this was all something we could really, truly do in a static type checking based way. But this just works. It works. It's worked for millions of developers in React. All right, so I'm sure you're probably asking then, you're like, okay, well, how do we do multiple writes? Like, that's great. You know, you're constraining the model, but at some point I do want to implement that e-commerce example. How do we do it? So what's the next programming kind that we can do? Transactions. Right? So this is how we do something like a bank transfer. Transactions take the current state, they can mutate the state directly, they can call other readers, writers, or transactions, and they return a response. Okay? So this code, this example of transfer, I hope is, this is what we were taught in CS 101 for if we wanted to implement transfer, and this is how we actually want to implement it in the distributed system too. Now, one of the things I think is really cool is that the minute that you have this power of transactions as a programming model construct, you don't need to do withdraw and deposit one at a time. You can do them in parallel. And it actually changes the way that you think about building applications where you can do things in far more efficient ways. All right, so what about that retry paradox? So we made idempotency a first-class primitive in the system, okay? So if you want to, you can explicitly make calls idempotently, but you don't have to. The reason you don't have to is because you can push the retries of the system all the way out to the edge, all the way out to the clients, which is where you want actually the retries anyway. So you can make things like the front end, this is just a little snippet of a front end making a call, actually be the thing that's responsible for doing the retry in an idempotent way. And I'll leave it as an exercise to the reader. You can imagine, based on all the other constraints that I put together with readers, writers, and transactions, you can guarantee that the events are only going to happen once. Okay? All right, so just a couple more slides, and then I'm all done. I said there's two things we want to do. We want to write data, and we want to read data. I kind of skipped over reading data the entire time, because isn't reading easy, right? Reading solved. There's nothing really to do for reading. The reality is it's not so simple, right? When you're reading data from microservices, you think it's going to be as simple as the picture on the left, but your microservices look like the picture on the right, and the number of different services you want to read from is a pain. But we figured out ways to call, lots of different ways to do it in parallel and call these over microservices and get it. Where it becomes prohibitively expensive and people just don't do it is when they want to try to get the data in a real-time way. You don't just want to read the data and get the data once. You want to call out to these things and somehow be able to get updates from all these different services. Doing this in a microservice-based architecture is so challenging, it's prohibitive. I don't see people doing it. And yet, the folks that are building the front ends, that's how they want the data. They want the data in a reactive, real-time way. So guess what? Side effect-free readers enable us to reactively make read calls. So it's just one of the really nice things that falls out of the programming model. So really quickly, what does this look like? When you go to execute one of these reader methods, we can effectively create the DAG of all the different things that you're calling. I missed one. All the things that are being called. And any time that the state changes anywhere in those places, we can re-execute that DAG and propagate the information all the way back up to whoever originally called it. So some people are saying, yeah, that's how I solved my reactivity problem. I just had to set up a whole separate system of subscriptions and all this other stuff, and we don't have to, just by constraining the programming model and having to be very, very clear which functions we're calling that are just readers versus writers versus the other things. All right. Last part that really falls out of this model is because we have all these independent state types, it feels kind of like you're developing a monolith. You're just, working with these data structures. But we can then distribute all those data structures however we want across all the resources in the cluster. So it kind of gets back to one of the things that I can't tell you how many times I heard from organizations that we're adopting cloud native, which is just let me write my monolith, just let me build my monolith. You get that experience of develop something like a monolith, but scaling like microservices. Okay, so hopefully I've demonstrated that we're not done yet in the cloud native ecosystem of thinking about how we want to make it easier for people to build applications on top. We don't want to throw the baby out with the bathwater. All the tech that we've deployed and put in place is good tech. We want to keep using it. But there's an opportunity to make it simpler for application developers building these apps on top, where they can focus on their business logic and not have to focus on all the problems from running it on top of Kubernetes. And that's it. Thanks.